Traditional latent action models compress visual transitions into a single flat vector. That inevitably entangles transition extent with transition mode. The entanglement forces the representation to absorb scale-related information, obscuring the structural priors downstream policies actually need. PoLAR solves this by imposing a polar geometry directly on the latent action space. It factorizes the transition into a radial coordinate for extent and an angular direction for mode. The model leverages temporal offset between observation pairs as a weak ordinal proxy for extent, pushing larger time gaps to larger radii. To make this geometry work, PoLAR lifts the inverse dynamics output into hyperbolic space via the Poincaré ball. The latent vector stays in Euclidean tangent space during quantization and decoding, but radial supervision happens on the manifold. Why hyperbolic? Because its volume expands exponentially with radius. This naturally gives angular directions exponentially more capacity to distinguish diverse transition modes as the temporal horizon grows. The representation is trained with two complementary losses, an ordering loss that anchors transitions to the start frame, and a radial margin loss that enforces strict monotonic radius growth relative to temporal offset. For discrete tokenizers, this translates to a factorized codebook. A single shared radial index is paired with multiple normalized direction indices per latent slot. On both simulated benchmarks and real WidowX manipulation tasks, PoLAR consistently outperforms flat latent action baselines and strong per-trained VLAs. It achieves higher mutual information with ground truth action chunks, keeps decoded action errors lower when tokens are mispredicted, and demonstrates significantly better cross-horizon gradient alignment. The takeaway is clear. When learning visual change representations, latent space geometry is a critical architectural choice, not an afterthought.